Okay, in the last module, we described the difference between technical variability, biological variability, and we explained the best way to perform inference to determine if a gene is differentially expressed in two strains. For each gene, we can compute a t-statistic. It doesn't matter if it's microarrays or RNA-seq. We can compute a statistic, and using the approximations that we described, either the central limit theorem or the t-distribution approximation, or some other approximation that for example, permutation test, something we're going to talk about later in another module, you can obtain a p-value. But now you have a p-value for each gene. So you have thousands and thousands of p-values. So how do you decide, of all these genes, which one do I report? Which of these genes is differentially expressed? So here are the results if we perform a t-statistic on the data that we described in the last module, and we use the t-distribution to obtain p-values. We get 1,578 genes that have p-values less than 0.01. We get almost 3,000 genes that have p-values less than 0.05. So is that the end of the story? We just report this and we're done? Well, it turns out that this is a little bit confusing and deceiving if we do it this way, and we're going to explain why that is. So for the next results that I'm showing in this slide, I permuted the samples. So I shuffle them around, eliminating the strain differences completely. So when I shuffle them around, then the null distribution has to be true. There's no difference. It's randomly split into two groups. When I do that and I follow the same procedure, obtain a t-statistic, compute its p-value, I get 79 p-values that are less than 0.01 and 840 p-values that are less than 0.05. So now that appears to not make sense, but it actually does, because when you're looking at thousands and thousands of genes, there are going to be 5% or so p-values that are less than 0.05 by chance. That is, in fact, the definition of the p-value. That, you know, it's the probability of observing something this big as 0.05. If we do 10,000, then 5% of 10,000, which is 200 genes, are going to be are going to appear to be differentially expressed if we don't interpret this properly. So in a later module, we're going to talk about how to deal with this. It's something called the multiple comparison problem. It's a little bit more technical, and we're going to cover it in another module. But that's something for this module. I want you to be aware that this is the case, that this is something that happens. So just one plot I want to show you that can help you understand this issue is the histogram of p-values. So here on the left, this is the histogram of p-values when I compare the two strings. On the right, I have a histogram of p-values when I shuffle the data. And one thing you see is that it's flat. It's close to flat. And that's actually what the theory tells you should happen. The theory tells us that if you have the null hypothesis being true for every single gene, then the distribution of p-values has to follow a uniform distribution. Any two intervals of the same size have the same probability of appearing. So what that tells us is that there are going to be some genes that have p-values less than 0.05. There's going to be some genes that have p-values less than 0.01. If you're testing enough genes, you're going to have a few genes that have p-values less than 0.001, etc. Right? They're spread all throughout the range from 0 to 1. Now, one thing we see on the left is that there's a higher number of genes down here. That's because we think that there actually are some genes that are really differentially expressed. So we have the flat histogram for all the genes that aren't differentially expressed. And then we have, on top of that, the ones that are, and they're all concentrated here on the left because they have smaller p-values. So this is a useful plot to make. Another related useful plot is the volcano plot. So what is a volcano plot? So what we do is we take the observed effect size. In this case, the effect size is the numerator of the t-statistic, which is the log ratio of the average gene expression values. And then on the y-axis for each gene, we plot the p-value, but we put it on a scale that makes smaller p-values go up. And the scale is we take the log base 10 of the p-value and we take the negative of that. So a p-value of 0.01 would be a 2. A p-value of 0.0001 would be a 4, etc. So what does this tell you? So a point around here had a fold change of about 8. That's a big fold change, and it had a p-value of about 0.001. So that's probably a gene that is really differentially expressed between these two strains. Now, when we make this plot, we see something new. We see a lot of points that have very small p-values. This is a very small one here. It's almost 1 in a million. But the effect size is tiny. The fold change is less than 50%. It's less than 25%. So do we really believe that that's something worth reporting? Well, one of the things we're going to learn in a later module is to use improved estimates of the standard deviation, improved estimates of the standard error using the t-statistic. The t-statistic is actually not a very good approach to finding differentially expressed genes, especially when you have small sample size. The reason being that the denominator is very variable, and you can get, by chance, very large t-statistics only driven by the fact that your denominator was very small by chance. So that makes the t-statistic not very powerful. We're going to explain that in a later module. We're also going to give you ways to improve on the t-statistic.